Alright, hello and welcome back to Probabilis. As always, I am super excited to be here and I am happy to have you with us. If you're joining on Twitch, welcome. Feel free to leave your questions in the comments as we go along and I'll try to get to them. And if you're watching on YouTube, feel free to join us live on Twitch for our next stream. And you can follow us at twitch.tv/Probabilis. So today is Wednesday, September 22nd, 2021. Unfortunately, it's not the night of September 21st, the 21st night of September. That was yesterday. But it being Wednesday means we are focusing on calculus today. And this lesson is going to be a lot of fun because now we're getting into the meat of calculus. Last week, we talked about limits. And while limits are very, very important to our understanding of calculus and the theory behind it, many of you may have been familiar with limits already, perhaps from previous classes. Now we're really getting into calculus, what it is. And today we're going to start our lesson on derivatives. So let's get into it. So when we think about calculus, there's usually two big words that summarize calculus. One is derivatives, the second is integrals. And integrals we will talk about much later in this course in a few weeks. For now, we're going to be focusing on derivatives. And this is a huge chunk of calculus. And it's super important to understand it, so that way we can do more complex things. But yes, we're going to be talking about derivatives. It's going to be a two-part lesson. So this week we'll do the first half of the lesson, next week we'll do the second half of the lesson. And I think this week is a little bit longer, but let's just get into it. So derivatives, chapter 2, let's do it. And the first section will just be an introduction to derivatives, and then we'll get more into it. So as always, we will start out with our definitions. So first of all, many of you are wondering, what is a derivative? And well, the derivative of a function allows us to find the slope of the function at a point. So, if we evaluate the derivative, whatever that means, of a function at some point, it will provide us the slope of the function at that point. And you might be thinking that's kind of weird because how can you take the slope of a point? But really, more specifically, it allows us to find the slope of the tangent line at a point on the function. So let's just say I have my axes here, right? And then I have some sort of function like this. And I want to find the slope of the tangent line at that point, right? So if we zoom in here, the tangent line looks something like this at that point. So evaluating the derivative will tell us what is this slope. What is that slope? And that might be a little weird, like why do we really care? I know that's the thing that I thought when I first learned derivatives, like why do we care about the tangent line and more specifically the slope of it? We'll get into that. But first, let's go over some notation for derivatives. So you'll commonly see f prime of x, or dy over dx, which we commonly just say dy dx, or y prime. So f of x, if we have some function of x, like f of x equals x squared plus 3x, something like that, f prime of x, that tells us what the derivative is. And, well, we don't know how to compute that yet. Dy dx is the same thing, and y prime, and this is more common when we see y as a function of x. So maybe y equals 2x cubed plus sine x, something like that, right? So then the derivative would be dy dx equals something, or y prime equals something. So if you see an apostrophe, which we call prime, or dy dx, that means we're working with a derivative. And now we get into the definition of a derivative mathematically. We understand the semantics of it. Let's look at the mathematical meaning. So we're taking the limit as some variable h approaches 0 of f of x plus h minus f of x all over h. So we're familiar with like f of x, right? That's just evaluating some function at a point x, right? So in this example up here, f of x would just be the function value of the point that I highlighted. So that's the second term here, right? Now we're introducing this variable h, which you can think of as like height, or just some little bit. And we're evaluating the function at that point. So the original point plus some value. So let's say it's a positive value. And if we go back to this example, x plus h will take us to like somewhere over here, right? And then f of x plus h is the function value. So that would be something up here, right? So this is f of x plus h, where h is just some displacement value. So we're evaluating the function at two different points, subtracting them, and then dividing it by how much we displaced by. So this should look very familiar. Maybe not, I mean the notation's kind of weird, but if you think about it, we're just computing the slope, right? We evaluated the function at some point here, and then some other point up here, and then we're taking the difference of the function values, which is the height, right? The difference in y values, essentially, and then dividing it by the change in x, right? So that's the h. So we're taking the limit as h approaches 0 of the slope. And we can see this better here. I like to think of it in this definition, the limit as delta x approaches 0. So delta x is a change in the x position, right? And it's the same definition except the h's are delta x's. And the important thing to see here is that this value of delta x is going to 0. It's approaching 0. So it's very, very small. Like, if we zoom into this, I was saying like, okay, x plus h could be here, and then f of x plus h is up here. But really, delta x is approaching 0. So we're getting extremely close to this. Like, this would be delta, or x plus delta x. And then we evaluate the function. So we're barely moving up the curve. And we're evaluating the slope there. And we can see that if we do it close enough, if delta x is really tiny, that would be essentially finding the slope of the tangent line, because we're only displacing by such a little amount. And that's seen better here with this visual representation, right? So this is some point evaluated on the function, and then we go over delta x, so that's x plus delta x. We evaluate the function at this x coordinate, which takes us up here, and then we take this point, the y value of it, we subtract the y value at this point, and then divide it by delta x, which is this much. So when we subtract the function values, we get this delta y, and then we divide it by delta x. So what we're doing is rise divided by run, which is slope. And we can see here, delta x is quite big, but as we get a smaller and smaller delta x, eventually as x approaches 0, our tangent line is there. You know, here, this isn't a very good tangent line at this point, but as it gets smaller, it's getting closer to the tangent line to that point. Here, it's super close to the tangent line. Finally, when delta x is really small, then we get the tangent line we want. And this is essentially the same thing. Delta x is gradually getting smaller and smaller until it approaches 0, and then we get the tangent line. So this is a really nice visualization of what a derivative is. It's just finding the slope of the tangent line at a point. So now we're going to put it all together. Okay, so the definition of tangent line with slope m. If f is defined on an open interval containing c, and if the limit of the limit as delta x approaches 0 of delta y divided by delta x equals limit as delta x approaches 0 of this, which is basically what we saw, the limit definition for a derivative, except now we have this c term here, right? Because we're in an open interval containing c. So this is really the point that we care about. So if that limit, if the derivative equals m, then that's telling us that there is a line that passes through c and where it's evaluated on the function with a slope m, and that is the tangent line to that graph at the point c. So this is just reiterating what we've stated before. It's just saying that if we evaluate the limit, if we evaluate the derivative, and we get a slope here, then that tangent line exists at that point with that slope. So hopefully that makes sense. So now we'll deal with the first question. But before we get into that, I'm just going to set up something. And right now we have a limit definition. So we've seen previously that limits are kind of annoying to deal with, especially when they can get kind of complicated. So I will say that there are easier ways of evaluating derivatives, and we will be getting into that shortly. But for now, it's important to understand the limit definition of it, so that way, we really have a good idea of what's going on graphically. And I hope seeing the visualization of the graph will help us out. Anyways, let's go back to the problem. So this is asking to find the slope of the graph of f of x equals 2x minus 3 when x equals 2. So slope of the graph, this just means the slope of tangent line. Slope of tangent. And we have this function, f of x, and we have the point where we're curious where the tangent line is. So, let's see. We're going to use the limit definition of a derivative. So the derivative is the limit as delta x approaches 0 of f of x plus delta x minus f of x, all of this over delta x. So what is f of x? That's f of 2, because that's the point where we want to evaluate the limit at. So where we see an x, let's just substitute it 2, so that way, we can kind of see what we're doing. So this is equal to the limit as delta x approaches 0 of f of 2 plus delta x, minus f of 2, all of this divided by delta x. Right, so we should be able to think about the visualization that we're at some point 2 comma f of 2 on the function, and then we're going to move over just by the tiniest amount, this tiny delta x. And then from there, we can, see what the slope is. Okay, so let's just go off to the side here. F of 2, we can compute this pretty easily. That's just plugging it into this function here, this function. So let's just do that. 2 times 2 minus 3, that's equal to 1. Okay, so that makes sense. Now, what is f of 2 plus delta x? Well, it's the same thing as what we did here, except here we had, this is a function of x, right? So where we see this x, we plug it in here. So whatever the input is, we plug that input where we see an x. So that's what we're going to do. This is equal to 2 times the quantity 2 plus delta x. In fact, let me just make this a little bit clearer, and we'll use a different color for this, just so we can see how it's being plugged in. That's not right. We're plugging in 2 plus delta x. So here we see the x, so we put this 2 plus delta x, and then finally the minus 3 comes along for the ride. And we can see that this is equal to 4 plus 2 delta x. I just realized the purple is a different color. That's okay. Minus 3. And that is equal to 2 delta x plus 1. Right? Great. So now we can come back to here. The limit as delta x approaches 0 of, f of 2 plus delta x, that's equal to 2 delta x plus 1 minus f of 2, that's equal to 1. All of this divided by delta x. So this we can further simplify. Limit as delta x approaches 0, 2 delta x, then we have this plus 1 term minus 1, so that's just 0, divided by delta x. And then we can see that, okay, this cancels with this, and now we are left with the limit as delta x approaches 0 of 2. And when we have a limit at a constant, that is just equal to 2. and that is a review from the last lesson where we evaluated limits. So we are saying that the slope of the graph of f of x equals 2x minus 3 equals 2. Now, does this make sense? Well, let's take a peek, right? So we're going to draw a set of coordinate axes here, and we can graph this 2x minus 3, right? That's just a line. So the y-intercept is -3, and then we have a slope of 2, right? That's just slope-intercept form. And we're saying that the slope at some point here, x equals 2, the slope of the tangent line there should be 2. Well, what is the tangent line at that point? Really, it's just the line that it's a part of. It just so happens that we're working with the linear function. And the slope of this green line is 2. So the slope here should be 2 as well, and that's what we got. So it makes sense conceptually, right? But we can see that when we deal with more complex functions, we won't be able to tell graphically just by looking at this line, saying that, oh, since we're on a line here, the slope must be the same. And, you know, if we were dealing with a quadratic function, a cubic function, something like that, we can't just say that, oh, it's the same, right? We'll need a different technique. And doing the limit can be kind of annoying. So now we have find the slope of the tangent line to the graph of f of x equals x squared plus 1 at an arbitrary point. So this is doing the same thing, right? We're finding the tangent line, the slope of it, and we have a function, but this time it's at an arbitrary point, not a specific point. So what does that mean? If we go back to this definition here, we had f is defined on an open interval containing c. So, and we just had the derivative definition in terms of this variable c. So that's the formula we're going to use, and we'll see how that helps us. So let's start by writing it out. The limit as delta x approaches 0 of f of c plus delta x plus, sorry, no, it's not a plus, it's a minus. I always mess that up. All of that divided by delta x, right? So that's the equation we have. So let's evaluate the two parts of the numerator, right? We'll start with f of c. Well, let's just use this equation we're given and plug in c. So this should be equal to c squared plus 1, right? We're taking this c here, and we're just putting it into here, right? Because this is f of x, so think of it as f of c should be c squared plus 1. Similarly, f of c plus delta x, we just plug in the c plus delta x where we see an x. So this is equal to c plus delta x squared plus 1. And we can expand this out. This is c squared plus 2c delta x plus delta x squared plus 1, right? That's just multiplication of polynomials, stuff like that. Great. So now we can go back to our limit and see what happens. So limit as delta x approaches 0, and the first term is this c squared plus 2c delta x plus delta x squared plus 1 minus f of c, which is c squared plus 1, all of this over delta x. So let's simplify the numerator a little bit. So what we see is we have this c squared term and a minus c squared term, so those terms cancel. So that cancels with that. And then we have this plus 1 term and then a minus 1 term because the minus sign distributes, so that cancels with that. So we're just left with 2c delta x plus delta x squared, all of this over delta x. And well, from the numerator we can factor out a delta x, and that helps us get 2c plus delta x all over delta x. And now we see that these delta x's canceled, and we're left with limit as delta x approaches 0 of 2c plus delta x, right? And well, we can, simplify this a little bit further, but maybe you can eyeball it. But this is really equal to that limit plus this limit. And the second one should be pretty easy to solve, right? Delta x is approaching 0, and we want the value of delta x as it's approaching 0. So this goes to 0, And this, well, it's not dependent on delta x, right? 2c is just some constant because c is an arbitrary point. So it doesn't depend on delta x. So this is 2c plus 0. So our answer is 2c. So that's just saying. Let's put it into context. At an arbitrary point c, say c equals 3, the slope of the tangent line at c equals 3 is 2 times 3, which is 6. And what do I mean by c equals 3? Really, I kind of mean x equals 3. Like, if we put 3 in here, we get the 3 squared plus 1 is 10, right? So we're at the point 3 comma 10 on the graph. At that point, if we take the tangent line there, the slope will be 6. And I have this nice little video here, which will animate something, and we will see it. Let me get it set up though. This will give a nice visualization of the... Okay. All right, let's see what's going on. Okay. So we have this function, and now there's this point, and it's moving along the function, and the number next to the vector, or the arrow, is the slope. It's telling us what the slope is. I'll play it again. Right? So watch it carefully. We can see that as x gets larger, the slope increases. And this makes sense because it's a quadratic function, right? This is in fact the function x squared plus 1. And I'll play it one more time, actually. Watch what happens when we get to, let's see if I can pause it. Okay, so right now, it seems like our x value is in between 1 and 2, right? Like 1.5. And it's saying the slope at that point is 3.27. Does that match what we got? It does, because we said the slope is 2 times c, or the x-coordinate. So if we're at x equals 1.6, then yeah, that certainly makes sense. So that's a really good sign. And axes are a little bit distorted. That's what happens when you do like computer programming like that. But yeah, hopefully that convinces you that we are in fact correct with our answer. All right, let's get back into it. So now here's some more definitions, but these definitions we just need to get them out of the way. They should be pretty obvious. First, the process of finding a derivative is called differentiation. Great, so now we have a word that we can use when we're finding the derivative. We're differentiating. So we have a verb. Next, derivatives can be used to find the instantaneous rate of change of a variable with respect to another. So this should make sense. This is actually extremely important. Derivatives give us rate of change. Because after all, that's what slope tells us. That's telling us how the x and y values are changing on the graph. We're measuring the change in the y variable, and we're dividing it by the change in the x variable. So that's essentially what derivatives are. They're a rate of change. You know, first we said they were the slope of the tangent line, which it is, but more importantly, they are a measure of the rate of change. And in this case, it's the rate of change at an instant, at some point along this curve. How are the variables changing? Cool. Next, we say a function is differentiable at a point x when its derivative exists at x. So that should be pretty self-explanatory. If we can find the derivative at some point, it's differentiable at that point. And the derivative exists if like the limit doesn't go to infinity, if there's no discontinuity, stuff like that. Okay, we are experiencing a little bit of technical difficulties, so I'm going to take care of that, and we'll be back in just a moment. Okay, we're back. So yeah, we went over the definition of differentiable, and we can further apply that definition to say that a function is differentiable on an interval now, an interval a to b, when it's differentiable at every point within that interval. So the first definition here, this one's talking about at a point, this one's talking about an interval. So it's just at all points within that interval. So those are some pretty basic definitions. It's just different forms of the word differentiable, stuff like that. So now we move on to section 2, differentiation rules. So now we will learn some tricks so that way we don't have to use the limit definition every single time, because you can see that would get really annoying. So as I just said, we'll learn how to find derivatives of some functions without direct use of the limit definition. And keyword is some functions. Some tricks will apply for certain functions while they won't apply for others, but as we progress, we'll see. So first is the derivative of constant functions. So the derivative of a constant function is 0, and that is if c is a real number. So that's just saying the derivative, so this is our notation when we're taking the derivative of something. So we saw a dy dx before, which looks similar, but that would say that the derivative is. This is saying this d dx means we are taking the derivative of this function c. That's saying the derivative of c equals 0. And this should really make sense, right? So let's sketch the Cartesian plane once again, right? And we have some function, which is a constant function at a real number. So let's just say c equals like 5 or something, right? And it's a constant function, meaning no matter what x is, it's always the same. Doesn't make sense for the derivative to be 0. Yes, because no matter where you are on that curve, the tangent line will always be 0. You rise 0 and you run, well, however much you want. Rise over run, that's slope. So when you rise 0, the slope will be 0. And we can see a nice proof of it over here, but I'm not going to dive into that for the sake of time. And yeah, you can read that. So if we see a constant function and we're taking the derivative, we know it's 0. Cool. Next is the power rule. This is really important. This one's so important. Oh my gosh, we use it all the time. All the time. So n is a rational number. That's key already. Rational number. Meaning it doesn't need to be an integer. It can be a fraction. Then, if we have the function x to the n, x is raised to the power n, that is differentiable, and the derivative of that equals n times x to the n minus 1. Okay. And that's just, at the bottom part, it's just saying n must be a number such that x to the n minus 1 is defined on an interval containing 0, right? Okay, and then the proof of that is here, but let's not really get into that. So what's going on here? Let's do it with an example, right? Let's say f of x equals x cubed. That is saying n in this case is 3, right? That's the power, and 3 is a rational number. That is saying the derivative of this, d dx of this, is equal to n, which is 3, times x to the n minus 1, which is 3 minus 1. So that's saying the derivative equals 3x squared. And we call that the power rule, because we're dealing with the power. So this one's super important. You can just think about it as you're bringing the power down, right? You're bringing this power down in front of the x, and then you're changing it to subtract 1, so it becomes h2 here. So this becomes 3x squared, right? And we can do it with another example here, x to the 5th. We bring the 5 in front, right? So this should be 5x, and then we change the power, and we subtract 1, so that becomes a 4, right? Cool. So now the question. Find the slope of the tangent line to the graph of x cubed, f of x equals x cubed, at x equals -1, 0, and 1. Well, we kind of just did x cubed. I kind of spoiled that. But anyways, let's just do it again. F of x equals x cubed, right? So the derivative, which we can represent it as f prime of x, that's an important thing, and I'm going to pause here. we're taking the derivative of the function, and the derivative produces a function if we are taking the derivative of a function. So we're ignoring evaluating it at a point. When we take the derivative, it will provide us a new function, which will give us how to find the slope of the tangent line. So here we apply the power rule, so n times x to the n minus 1, so that's equal to 3x squared. So what does this mean? This means at some point x, if we put it into this function f prime of x, we just put the x value in there and evaluate it, this 3x squared, whatever that value is, that's the slope of the tangent line. So let's do it. We are asked to find it at x equals -1. So f prime of -1, that equals 3 times -1 squared. And that's just equal to 3 times 1, which is 3. F prime of 0 is next. That's equal to 3 times 0 squared. And that's just equal to, well, 3 times 0, and that's nothing. F prime of 1, right? 3 times 1 squared equals 3 times 1 equals 3. So these are the slopes at the points respectively. At x equals -1, the slope is 3, tangent line slope is 3. At x equals 0, slope is 0, and so on. And I have another video here, and unfortunately, it doesn't show a -1, but it'll show what happens as we go to 0 and 1, and really pay attention to what the slope value is. So let's play it. So at 0 right now, the slope is 0. Now as we get to 1, now it's 3, right? So we saw what happened, and as we get, to larger values of x, the slope increases at a faster rate. And we'll play it one more time, right? I'll try to pause it. Right about here, right? We can see that we're very close to x equals 0, and it's telling us that the slope is like 0.00. I think it says a 6, it's kind of hard to see. But anyways, it's extremely small, it's close to 0, right? And that's what we expected. And I'll try to pause it one more time here. Right? We're basically at x equals 1, ignoring like the pixels of computers and stuff like that. We're very close to it, and it's telling us the slope is 3.05. So we should be feeling really good about ourselves. So that's pretty cool, I think. Yeah. All right, so let's get back to the presentation and continue where we left off. Cool. And you can see that there's another black box, which means another video. I had a lot of fun time making those videos, so hopefully you enjoyed them. Now it's asking us, find the derivative of f of x equals 1 divided by x squared. And at first we must be like, what? It kind of looks like the power rule, right? Because the power rule was of the form x to the n, but we have it in the denominator. And then you must be like, wait a second. That's the only trick we've learned, right? Either we're going to use the power rule, or we're going to use the limit definition. And we're not going to use the limit definition. We're going to use the power rule. And the reason is that this expression here can be rewritten as the form x to the -2 power. That's what negative exponents do, right? They make it 1 over x to the positive value of that power. So this is actually a really important technique that I hope you become familiar with, because this will help us a lot throughout calculus. In fact, you'll do this numerous times, so make sure you're able to switch back and forth between fractions with positive powers and just variables with negative powers. So with this, now we have f of x equals x to the -2. Now we can use the power rule, right? Because when f of x equals this, we know that f prime of x equals n times x to the n minus 1. So we'll do the same thing. F prime of x equals -2, that's n, times x to the -2 minus 1. So that's equal to -2x to the -3, or if we want to be fancy about it, -2 over x cubed. And it just asked us to find the derivative. It didn't ask us to evaluate it at any points, but if we wanted to, we could. So what's the derivative at x equals 1? Well, you plug a 1 into there, you get -2 over 1 cubed, that's equal to -2. What's the derivative at 0? negative 2 over 0 cubed, well, that seems a little bit problematic. So maybe we would conclude that the function is not differentiable at x equals 0. And in fact, it's not. And let's just take a look at the video. I'm going to pull it up, and we'll be able to see quite clearly why it's not differentiable at x equals 0. So we have the axes, and now we drew the graph, right? And before the point moves, we can see that as x is getting closer to 0, it seems like we're approaching infinity, right? It's shooting upwards, so maybe there's a vertical asymptote there. And if you remember the function 1 over x squared and what we talked about last week, when the denominator is 0, there's likely to be a vertical asymptote, so it makes sense. So we can't compute the derivative there. So let's watch what happens. We can see that the slope is increasing, now it's getting really, really big, and then as we come down, it started out as a really negative number, but now it approaches 0. So why does it approach 0, right? Why was it approaching 0 as we got to like x equals 5, x equals 6? Well, I mean, you can think about it. The limit as x approaches like some positive number, let's just say 10, of negative 2 over x cubed, well, that's just equal to, by direct substitution, negative 2 over 10 cubed, and that's just negative 0.002, right? So as x gets larger here, this denominator gets really, really large, and we're dividing by a huge number, so we'll get closer to 0. Right, so this would just be the limit as x approaches infinity of negative 2 over x cubed. That equals 0. So that's why I said limits are super important that we understand correctly. Alright, let's move onwards. The constant multiple rule. So if f is a differentiable function, and c is a real number, then c times f is also differentiable, and the derivative of c times f of x equals c f prime of x. So on the right is just some proof that you can look at if you want to, but that's just saying from here, what we're taking the derivative of. If c is just some scalar value that we're multiplying with, we can just take it out in front. This is saying that this is equal to c times d dx of f of x. And there is a reason for this, except I can't explain it right now because the reasoning is based off of something we'll learn a little bit later on. But that's just saying if you have a constant multiplied to a function of x, we can just take out the constant when we're computing the derivative. And so we can see that at the bottom here when we're doing the power rule, right? We're combining the constant multiple rule and the power rule. So if we take this, the c out front, right, this would be telling us this is equal to c times d dx of x to the n, right? And that makes sense here. That's c, and this term right here, that's the derivative of x to the n, right? And then we're just multiplying it together. Cool. Let's do some questions. So now we're asked to find the derivative of 5 over 2x cubed. Okay, so I know I just said that we should be careful when we see powers in the denominator, and we will be careful. But let's do a little bit of simplification first. So y equals 5 divided by 2x cubed. Well, that's just the same thing as saying 5 divided by 2 cubed times x cubed, because the entire quantity in the denominator is getting cubed. And well, that's equal to 5 over 8 times x cubed. And more importantly, that's, well, let's just split it up into 2 different fractions, right? So now we have this x cubed term in the denominator, and let's now make it a negative power. So this is equal to 5 over 8 times x to the negative 3. And now we'll use the rule that we just saw above here, right? This is the constant multiple combined with the power rule, right? So this is saying dy dx, well, I'll just write it out. This is the derivative of 5/8 times x to the negative 3. And the constant multiple rule told us that, well, we can pull out the constant, which in this case, the constant is 5/8. We're going to pull that out in front, and we're going to multiply that with the derivative of x to the negative 3. So now we keep this constant along for the ride, and now we evaluate this using the power rule. So the power n equals -3, so we bring that out front. X stays, and then we reduce the power by 1, so that becomes -4. Then we can evaluate this some more. This times this, that's -15/8 times x to the -4. And if we want to be fancy, that's equal to this. So that's the derivative. And once again, what does that mean? That means at any point x, we can plug it into this -15/8 x to the 4th, and that'll tell us the slope of the tangent line at that point. All right. Next, we have the sum and difference rule. So if we have the sum or difference of two differentiable functions f and g, that itself is differentiable. And the derivative of the sum or difference is the sum or difference of the derivatives of the individual functions, right? So if we take two functions and we take the sum of them, and we can do that like point-wise, that's how functions usually add. When we take the derivative of that new function, that's the equivalent of taking the derivative of the first function and adding it to the derivative of the second function. So you can sort of think about it as like a distributive type thing, that the derivative function is, distributing to each individual function. That's a fine way of thinking about it, and we can see that here, right? It's sort of distributing, and this minus sign stays there. So this should make more sense with an example, right? So find the derivative of this. I won't read it out. But you can sort of see, like, if this was f of x, and this was g of x, and this was h of x, then we could use, like, this rule up here, right? Where the sum and difference is distributed. So I'm just going to do that all in one step, but this is just saying that f prime of x equals the derivative of -x to the 4th over 2 plus the derivative of 3x cubed minus the derivative of 2x. And these are all power rule type things. So let's do the derivative of the first term first. So -x to the 4th over 2. That is, I'll just write it a little bit cleaner so we can see how we're using the power rule and constant multiple. That's the derivative of this. So the constant comes along for the ride, and I'm going to compute the derivative of x to the 4th now. So by the power rule, that's equal to 4 times x, and then we lower the power by 1, cubed. So that's just equal to -2x cubed. Now we can do the second term, so d dx of 3x cubed. So that's equal to 3, the constant stays, and then we do the power rule, so 3x, and then that should be 3x squared. That's the derivative of x cubed. So that's just equal to 9x squared. And then finally we compute the derivative of 2x. And that, well, the constant stays, and then we can use the power rule, right? X to the power of 1, that's equal to 1 times x to the 0. X to the 0 is 1, so this is 2 times 1 times 1. That equals 2. And now we put it all together, right? So f prime of x now equals -2x cubed plus 9x squared minus 2, right? We're just taking these terms here. And then you can just write that a little bit neater if you want to. So that is our derivative. So that's just saying find the derivative of each individual term and then add or subtract them if needed. So now we'll move on to some trig derivatives, because functions can be of trigonometric functions, right? We're familiar with sine x, cosine x. And this is telling us the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. I really wish the derivative of cosine of x would be positive sine of x, but it's not. So now you have to remember, oh, is it cosine that's a negative sine, or is it sine that goes negative cosine? That's why I mentioned down here, it's a good idea to have these memorized. It just helps in the long run. So yeah, pretty basic slide, but it's important to know these. Okay, now let's really hone in on the rates of change, right? So I mentioned earlier on that derivatives are a measure of rate of change. And so we can look at it a little bit. You might be familiar with this equation, distance equals rate times time. And if we solve for rate, because that's what we're interested in, that's the distance divided by time. So let's put it into context, right? If we start at some position x naught and time t naught, and this object at that point travels to some final point xf, x final, at time t final, then the velocity, which is a measure of the rate of change of distance, is given by this equation. The difference from the final position to the initial position divided by how much time has elapsed. And this equation looks eerily similar to the equation for slope, because it is. It literally is slope. Velocity is the derivative of position, right? We are changing position and we're measuring the time. It's a measure of rate of change of something. So if you study physics, you're familiar, velocity is the rate of change of position. Acceleration is the rate of change of velocity. So you might start to think that, oh, acceleration is the derivative of velocity. Maybe it is. And then the previous equation, this one that I bracketed here, that gives us the average velocity of the journey, right? Average velocity. Okay, so now this is sort of like a physics problem, but we do see a lot of physics problems in calculus, calculus BC. So we can read this. A ball is dropped from a height of 100 feet. The ball's height s at time t is given by the position function, which is that. So now it's asking us, what is the average velocity over some time interval? In fact, 2 time intervals. And then what is the velocity of the ball before it hits the ground? Okay. So we just went over average velocity, right? Average velocity, and I'll simplify it a little bit. We said that it was the change in position, and I'll use the symbol delta for change, divided by the change in time. Okay, well, let's deal with this time interval first, 1 to 2, right? Well, the change in time for that should be pretty simple, right? That's just equal to the final time minus the initial time. But what's the change in position? Well, we're given the position function above as a function of time. So we can compute the position at those 2 points and then just subtract the values. So I'll say like s of 1, right? S is a function of t. That's equal to negative 16 times 1 squared plus 100. So that's just equal to negative 16 plus 100, which is equal to 84. And then we also want to compute it at the final point, so that way we have a point of comparison. And we do the same thing, except now we put a 2 in here, right? So this comes out to be negative 64 plus 100, and that is equal to 36. And now we want delta of the position, the change in position. And if we remember, that's the final position minus the initial position. So that would be 84 minus 36. And then if we compute that, that's 48 divided by 1. So that's saying that the average velocity is 48, but we do have to include units. It's very important. And we are given that the ball is dropped from a height of 100 feet. So it's traveling at this many feet per second. It didn't mention that we were measuring it in seconds, but we'll just assume we're in seconds, right? Because, and this unit should make sense if you haven't studied physics. We can think about it logically. Position is measured in feet, time is measured in seconds, and then we're dividing them, so feet per second. So that's part A. Part B is very similar. Our starting point is the same, we just have a different ending point. So let's evaluate s of 1.5. So that's negative 16 times 1.5 squared plus 100. And that gives us, let's just see, that gives us 64. Right? So now we can compute the average velocity. I'll use a symbol v bar. That's a common symbol we see for average velocity. So we do final position, which is now 64, minus initial position. So that would be 84 divided by 2 minus 1. And actually, I actually made a mistake up here. This is wrong. The final position is at this endpoint 2. So we actually start with 36, and from there we subtract the 84, because that's the initial position. So I got them mixed up. That's on my end. So the numerator is now negative 48, and this becomes negative 48 meters per second, or feet per second. And now it should make sense conceptually, right? Because the ball is falling to the ground, and typically we assign the positive direction to be upwards and the negative direction to be downwards. Velocity is a vector, so it requires direction. So it's going negative 48 feet per second. So it's going 48 feet per second downwards. All right, glad that's clarified. And then if we evaluate this, by the way, the denominator here should be 1.5, since we have a different time frame. If we evaluate this, this should give us negative 40 feet per second. So this is pretty interesting, right? From 1 to 1.5, the average velocity of the ball is less than the average velocity from the time interval 1 to 2. And we're just comparing the magnitude. Don't worry about the sign of it. And that might be a little confusing, but it actually makes sense. And this is mainly due to gravity, which provides an acceleration. And I won't get much into that, but if you've studied physics, you might be familiar with what's going on here. That acceleration provides a change in velocity. And in this case, it speeds the ball up. And then let's do the last part, which I'll just call C. And this is saying, what's the velocity of the ball before it hits the ground? So, what is the velocity of the ball before it hits the ground? So, before we were computing average velocity. Now we're computing velocity at a specific point right before it hits the ground. So we can't use this equation of change in position divided by change in time because we don't have anything to compare it to. So that means we must take the derivative of it. So that way we can get the derivative as a function of time, right? We can compute what is that rate of change at a specific point. So velocity of time, that's equal to the change in position with time, right? The derivative of s. And if we compute this, the derivative of negative 16t squared, you can use the power rule and the constant multiple rule. And if you do that, you'll get negative 32t plus the derivative of 100 is 0. So this is our velocity function. At any time t, the velocity is given by negative 32t. So at t equals some time, the velocity equals negative 32t. But we want to know the velocity of the ball right before it hits the ground. So when does the ball hit the ground? Ball hits ground, when s equals 0. The position is 0. And this makes sense, right? Because at t equals 0, the ball is just being dropped at a height of 100 feet. And if we put 0 into here, we get 100. So we want the time when the position is 0, when it's at the ground. So, well, let's just solve for it, right? 0 equals negative 16t squared plus 100. This tells us that 16t squared equals 100, right? And, well, t squared equals 100 divided by 16. T equals square root of this. And luckily we have a perfect square on the numerator and denominator. And this tells us at t equals 2.5 seconds, it'll hit the ground. Great, so now we can find the velocity at that time because v of 2.5 is equal to negative 32 times 2.5. And if you multiply that out, this will give us negative 80 feet per second. Okay, so that is this problem. I'll just box these answers. Right, so this is a good application of both average velocity and instantaneous velocity. This last one that we did is called instantaneous. Instantaneous. I hope I spelled that right. Because we're finding it at a particular instance. All right, let's move onwards. Find the derivative of y equals 1 over x minus 3 sine of x. Whoa, a sine term. Whoa, hopefully we remember what the derivative of that is. But anyways, first let's deal with this 1 over x term, right? So we can just say this is equal to x to the negative 1 minus 3 sine of x. So now we know that dy dx, the derivative, that's equal to the derivatives of the individual terms and then the difference of them, right, by the addition subtraction rule. So that's equal to that minus the derivative of 3 sine x. So first let's compute this first term derivative, and that's just using the power rule. So the power comes down, negative 1, x, and then the power decrements by 1, so that goes to minus 2. So that's just saying that the derivative is negative x to the negative 2. Next, we want to find the derivative of 3 sine of x, and we should remember that constants come out, so this is equivalent to this here. And, well, let's see, do we remember the derivative of sine of x? It's probably cosine of x. Is it positive cosine x? Is it negative cosine x? It's positive cosine x. So this is equal to 3 times cosine of x, and putting it all together, we get negative x squared minus 3 cosine of x. And that's our answer. Good. Let's do another one. Find the derivative of that. Whoa, what is that? Huh, there's no trig function in there. Maybe a power rule, but like there's an x in the denominator? That seems kind of weird. But anyways, let's rewrite it, right? F of x equals 4x cubed plus 2x plus 5. What are we going to do with this? All of this over x? Well, for this one, we're going to use a super basic technique that we learned many, many years before we studied calculus. But for some reason, a lot of people forget that you can do it when we're doing math. It's one of my favorite things in the world. Breaking apart fractions. We can just put this into 3 separate fractions, right? This is equal to 4x cubed over x plus 2x over x plus 5 over x, right? It's common denominators, and that's just how you add fractions, right? You just add the numerators and divide it by the common denominator. So we're doing that in reverse. And for some people it might be like, isn't that obvious? And for some other people it might be like, this is insane. Why didn't I think about it? And yeah, I love this technique. But now we can see that, oh, we can get some terms that cancel, right? Because this is equal to 4x squared plus 2 plus 5 over x. Okay, so this last term is a little bit annoying. But we have an x in the denominator, and we just worked with that in the previous question. So this is really equal to that. And well, we can just find the derivative of that now. So f prime of x, I'm going to go through things a little bit faster now because we're kind of familiar with how to take derivatives. So obviously it's the derivative of this plus the derivative of that plus the derivative of that. So that's equal to 4 times, then you do the power rule on x squared, we get 2x to the 1, plus the derivative of 2 is 0 because it's a constant. And then the last one, we do the power rule, but first bring out the constant. So 5 times negative 1x to the negative 2, because we decremented by 1. Simplifying this gives 8x plus 0 plus negative 5 over x squared, and just putting it all together, we get 8x minus 5 over x squared. And that's our answer. So now we're dealing with some more complex functions, and we're still able to find the derivative, and we only know just a few rules. So you can see that if we had to do the limit definition, this would just be an absolute pain. So it's cool that we have this. Okay. Given the distance versus time graph, sketch a corresponding velocity versus time graph. Oh boy. Oh boy. Okay. We have to sketch a graph. Whoops. Okay. So I'm going to draw my best set of axes that I can. Okay. The key thing to note here is that velocity is the derivative derivative of position. So really what we want to do is we just want to evaluate the derivative at all of these points on the function. 2, 4, 6, 8, 10, and same thing here. So we want to find the derivative at all of these points and then just graph it. So we'll say this is velocity, this is time, and this is 10, this is 2, this is 2, that's 10, right? Increment by 2. So let's do it. At this 0, 0 point, let me use this. What's the derivative there? It's the slope of the tangent line, and well, it's a part of a linear function. So the slope should be the slope of that linear function. And what's the slope there? Well, it goes from 0, 0 to 4, 2. So it rises by 2, runs by 4. So the slope is, well, it's a half, right? So actually, I'm going to change the bounds on this. Let's make this, let me add another one here. So this is 1, this is going to be a half, right? So at x equals 0, we have that the velocity is a half. Great, so what happens when we're right here at x equals like 1? Well, we're still on that line, so the slope is still the same. It's still a half. And in fact, any point along this line, we're still on the line, so the slope will be a half. So until x equals 4, the velocity is a half, and it doesn't change. Great, but then we get to x equals 4, and now we're on this different segment. But that's also a linear segment right there. The slope just happens to be different. In this case, it's 0, right? The rise is 0, the run is 2 in this case. So any point from 4 to 6, the velocity is 0. So 6 is here. So we're down here. Lastly, from time equals 6 to 10, we're on a new segment, and it's linear. So the slope of the tangent line is the slope of that line. And what's the slope there? Well, we have 2 points, 10, 6 and 6, 2. Slope equals y2 minus y1 divided by x2 minus x1. So that's equal to 6 minus 2 over 10 minus 6. So that's equal to 4 divided by 4 equals 1. So any point on here, the slope of the tangent line is 1. So we can graph that here. Say until 10, the slope is 1, the velocity is 1. So that's something what the velocity versus time graph should look like. And I'll draw these dotted lines here to show, I guess that wasn't a bad, this is a pretty bad drawing. But hopefully you get the picture of what's going on here. And the key thing is velocity is the derivative of position. Okay, so now we have another word problem type thing. So the volume, oh my goodness, I'm so used to saying velocity. Volume of a cube with sides of length s is given by v equals s cubed. Find the rate of change of the volume with respect to s when s equals 6 centimeters. Rate of change. That should be keywords for derivative. And, well, since we've only been talking about derivatives today, it makes sense, right? So we're given v equals s cubed. And we're like, okay, how do we find the velocity of that, right? Oh my goodness, the derivative of that. So used to saying velocity. Because we're used to seeing functions in terms of x. And, well, the same rules apply. It's just a different letter, right? This is equivalent to saying y equals x cubed. We're just saying that now x and s are the same thing, so x is like a side length, and y is volume. So let's find the derivative of this v equals s cubed. So now we'll say dv ds. Alright, so let's take a pause and look at this notation. We're taking, the numerator is telling us we're taking the derivative of v with respect to s. So the value that's in the bottom, the variable that's in the bottom, that's not d, is what we give the respect to, with respect to s. And that basically tells us that the function v is in terms of this value s. So that's just another type of vocabulary we see with derivatives. The derivative of volume with respect to s. And the same rules apply. This is equal to d ds, because we're taking it with respect of s cubed. And that's just a simple power rule. That's equal to 3 times s squared, just by the power rule. So that's saying the rate of change of volume when s equals some value is 3s squared. So what we're doing is we're taking this cube and we're stretching it and condensing it, and these side lengths are either growing or shrinking. And as we're doing that, we're curious, how much is the volume changing by? Right? Because obviously it changes. When you get larger side lengths, the volume gets bigger, right? So we're curious, how is that volume changing? And with this, we can compute it, right? At s equals 6 centimeters, the rate of change of volume is 3 times 6 squared. And that's equal to 3 times 36, which is 108. So what are the units on this? Well, we're studying volume, right? So we're changing the volume. So the unit should be cubed. And in this case, we're working with centimeters. So centimeters cubed, but it's a rate of change. So we're seeing how it changes with time. And so in this case, we're saying it's per second. So as we're changing it through time, and when the side length is 6 centimeters, the volume is changing by 108 centimeters cubed. So I think that's pretty cool. We see a nice application there. So now we see the wonderful product rule. This will help us out tremendously. And in fact, this is the reasoning to the constant multiple rule. So if you have two differentiable functions, f and g, that is itself, it itself is differentiable if f and g are differentiable. Moreover, the derivative of f times g is the first function times the derivative of the second, plus the second function times the derivative of the first. And we see that here, right? We're taking the product of two functions, we're taking the derivative, and we're doing first times derivative of the second plus second times derivative of the first. And the shortcut term that I learned is 1d2 plus 2d1. So d stands for derivative, 1 is the first function, times the derivative of the second, plus second times derivative of the first. So if I say 1d2 plus 2d1, you should know what that means. So let's do it. Find the derivative of this, 3x squared times sine x. Okay, so let's just say that, how can we represent this nicely? 3x squared sine x, that is equal to 3x squared times sine x. Obviously, right? We're just breaking it apart. And now it's the product of two separate functions which are themselves differentiable. So this is the first, this is the second. So by the product rule, f prime of x tells us that this is equal to the first, I'll just write the word first, times the derivative of the second plus second times derivative of the first. So instead of using these words, let's actually plug it in. So this is equal to 3x squared times the derivative of sine x plus sine x times the derivative of 3x squared, right? And now we can simplify this, right? This is what we've learned to do. 3x squared, and then the derivative of sine x is cosine of x. And then we're adding sine of x times the derivative of 3x squared. Use the power rule here. 3 times 2x to the negative 1. So that becomes 6x. And then we can just simplify this to say it's 3x squared cosine x plus 6x sine of x. And so one technique we can use is consider like f of x equals 3x squared. We've previously learned to do this as, constant multiple with the power rule, right? 3 times derivative of x squared, and then x squared becomes 2 times x to the power of 1, and then we combine it all together. But we can think about this as 3 times x squared. And if we do the product rule now, 1d2 plus 2d1, we get this is equal to 3 times the derivative of x squared plus x squared times the derivative of 3. And the derivative of 3 is 0. The derivative of any constant is 0. So the second term goes away, and we're left with 3 times the derivative of x squared. That's what we're accustomed to, right? That's the constant multiple rule, and we're combining it with the power rule. And that is equal to 6x to the power of 1. So that's just a brief aside. Now we're finding the derivative of 3x squared times sine x times cosine of x. And I'll just say that's equal to f of x. So it's kind of broken apart for us into multiplication, but now we're multiplying 3 things. So what we have to do is actually the power rule twice. So we can say that this is equal to, let's just group a couple of the terms together. So we'll group the first 2 together, times cosine of x. So now we'll use the the product rule on these 2 terms. So f prime of x equals 1 3x squared times sine x, 1d2, so that's the derivative of cosine x, plus 2, which is cosine x, d1, which is the derivative of 3x squared sine x. So let's try to simplify this a little bit. 3x squared times sine x stays. Derivative of cosine of x, that's negative sine of x. Don't forget the negative sign. Plus cosine of x. And then we have the derivative of 3x squared sine x, which we don't really know what it is off the top of our head. So I'll just keep it here for now. And, well, let's just compute that. And we can do that by using the product rule. d dx of 3x squared times sine x. That's just the product rule. We have one term here, and we have the other term here. So let's do product rule again. 1d2. 1 is 3x squared times the derivative of the second, sine x, plus 2, which is sine x, times the derivative of the first, which is 3x squared. So that's equal to 3x squared, derivative of sine x is cosine of x, plus sine of x times derivative of 3x squared. We actually just did this in the last slide. That's 6x. So this is equal to 3x squared cosine of x plus 6x sine of x. And then we're going to take this and we're going to substitute it back in here. And finally we get f prime of x equals, I'm going to combine all of this into 1. So this is negative 3x squared sine squared of x, because it's sine x times sine x, plus cosine of x times, now we're substituting this quantity in, 3x squared cosine of x plus 6x sine of x. And then we'll just do one last simplification here, just distributing the cosine in. We get 3x squared cosine squared of x plus 6x sine x cosine x. This can be further simplified, but it doesn't really matter too much. We kind of got the final answer, and that's our final answer. So we can see that already we're able to find the derivatives of these really complex functions, which is really exciting, because when we started out today, 70 minutes ago, we didn't really know all that much. So be proud of yourself. We've learned a lot. Now we do the quotient rule. So we just did the product rule, now we do the quotient rule. I'm not going to read this entire chunk, you can read it if you want. But now we're dividing 2 functions. And when we take the derivative of their quotient, we get this huge expression. And once again, we have another saying for it. Product rule is 1d2 plus 2d1. Quotient rule is low d high minus high d low all over low low. So what does that mean? G of x, that's low. F of x is high. So low is g of x. D high is f prime of x minus high f of x d low, which is g prime of x, all over low. So low is low times low, which is g of x squared, right? So that's the mnemonic I'm going to be using because I'm not saying that entire equation out loud. So yeah, let's just do a problem, right? Find an equation of the tangent line to the graph of f of x equals that at -1, 1. So tangent line equation tells us derivatives, and then we just have to evaluate it at a point. Okay, so let's just do it. So I'll just write off to the side our low, which I'll abbreviate LO, that's equal to x plus 5. And our high is the numerator, that's equal to 3 minus 1 over x. So f prime of x, and we can clearly see we're taking the quotient of something, right? We're dividing it. We're dividing two functions. So f prime of x equals low d high, I'll write it out, minus high times d low, all over, I suppose I should have used LO here, but all over low, which is low squared. So let's just substitute it in. We get x plus 5 times the derivative of 3 minus 1 over x minus 3 minus 1 over x times the derivative of x plus 5, all of this over low, which is x plus 5 squared. Right? So let's compute those derivatives. 3 minus 1 over x. Well, that's equal to the derivative of 3 minus the derivative of 1 over x, which is x to the negative 1. And the derivative of 3 is 0 minus, then we can do the power rule. We get negative 1 times x to the negative 2. So that's just equal to 1 over x squared. And then do a similar thing here, derivative of x plus 5, that's equal to derivative of x plus derivative of 5, that's equal to 1 plus, well, 0, so that's just equal to 1. So now we substitute it back in and we get f prime of x equals x plus 5 times 1 over x squared minus 3 minus 1 over x times 1, all of this over x plus 5 quantity squared. And, well, we can simplify this, but I don't really want to, because we're curious about finding the equation of the tangent line at negative 1, 1. So here, x equals negative 1. So let's plug in negative 1. F prime of negative 1 equals negative 1 plus 5 times 1 over negative 1 squared minus 3 minus 1 over negative 1 times 1, all of this over negative 1 plus 5 squared. Okay, so what do we get here? Okay, let me just double check to make sure we're doing this okay. Okay. So, this gives us, first term is 4 times 1 minus 3 minus negative 1 times 1, all of this over 4 squared, that's equal to 4 minus 4 over 16, which gives us 0. So that's our answer. And I wish I had a graph to show you, but unfortunately I didn't create a video for it. So now let's move onwards. Find the derivative of tangent of x. Ooh, exciting. We know sine and cosine. We don't know tangent. So how can we do this? We have f of x equals tangent of x. Well, how else can we represent tangent of x? That's equal to sine of x over cosine of x. And now we're like, okay, well, I can do that. I know how to do this. This is just the quotient rule, right? So f prime of x equals low d high, that's the first thing. So low is cosine of x times the derivative of high, sine x, minus high, sine x, times d low, which is derivative of cosine of x, all of this over low, which is cosine of x squared. And, well, I'm just going to do it directly here, but we get cosine of x, derivative of sine x is cosine of x, minus sine of x, times derivative of cosine x is negative sine x, all of this over cosine of x squared. And we can simplify this and we'll get cosine squared x minus negative sine squared x, all of this over cosine squared x. This is equal to cosine squared x plus sine squared x, all of this over cosine squared x. And if you remember your trig properties, the top part simplifies to 1, and the bottom part is cosine squared x, so we can just say this equals secant squared x. So now you know your derivative for tangent of x, and you'll want to memorize that. Okay. Yeah. Actually, we're gonna go back to this previous question because I didn't finish it. Find the equation of a tangent line. So make sure you read your questions. Right now we just have the slope, but this is pretty easy. Y equals mx plus b, right? That's just a line. We have the x coordinate, we have the y coordinate. That's -1, 1, right? Y equals 1. And we have the slope, m equals 0. So really, this is just telling us 1 equals 0 times -1 plus b, or really 1 equals b. So our equation is just y equals 0x plus 1. So y equals 1. That's the equation. So glad we went back to that one. So now I'm just giving you the remaining trig derivatives. You can derive them on your own. And like I said, they're all obtained by using the quotient rule. Cotangent is cosine over sine. You do quotient rule. Secant is 1 over cosine. Cosecant is 1 over sine. You can do the quotient rule, and you'll get these answers. And I suggest trying it out for yourself, especially like cosecant or secant. But yeah, memorize those. Yeah, you should. It'll save you a lot of time. So now we'll talk about higher order derivatives just briefly. So thus far we've only taken the derivative of a function one time. And the first derivative gives us the slope of the tangent line. So that's great, right? When we take the derivative, we get a function back from a function. But really, we can just keep on taking derivatives, right? Like if we go back to this and we have secant squared of x, why can't we find the derivative of that? Well, we can, right? We can do whatever we want. We're people. We can do whatever we want. So if we do this, then we start to explore higher order derivatives. And the meanings of these derivatives can be quite confusing. First derivative, it's kind of easy to understand, but it's already kind of complex. But don't worry, I know you're super excited about derivatives, and we will be learning about the second derivative in due time. It's coming up. But recall that we obtain velocity by taking the derivative of position. And we did this because velocity is a measure of change in position through a change in time. And this next point I alluded to. I'm asking what's the derivative of velocity? And that will be the change in velocity through a change in time. And that's what acceleration is. So acceleration is both the first derivative of velocity and the second derivative of position. Because the first derivative of position was velocity, but if we take the velocity or the derivative of velocity, we get acceleration. So that's the second derivative. So that's one cool application. All right, I think we're nearing the end. This is just the notation. Basically, all that we do is we add more prime symbols, or we do like d cubed y dx cubed, right? We just add the power there. So it's good to understand notation, just for mathematical clarity. Here we go. Find the derivative of the cube root of x times square root of x plus 3. Okay. So there's a couple of ways to do it. But let's do the product rule, right? Because we're multiplying two things. So let's just say this is equal to f of x then f prime of x equals, oh no, did the music stop? If so, let's get some music. Okay, that'll work for now. Okay, so we'll do the product rule. So 1d2 plus 2d1. So 1 is the cube root of x times the derivative of square root of x plus 3 plus square root of x plus 3 times the derivative of the cube root of x. So what's the derivative of the square root of x plus 3? Well, we haven't really dealt with square roots, but we can express square roots as powers, right? This is equal to the derivative of x to the 1/2 power plus 3. And now we can do the power rule, right? That's equal to 1/2 x, and then we decrease the power by 1, so 1/2 minus 1 is negative 1/2. And then the derivative of 3 is 0, so that just doesn't do anything. And then we want the derivative of the cube root of x as well. So we'll do a similar technique, right? This is equal to x to the 1/3 power. And then we do the power rule again, 1/3 x, then we decrement the numerator, the power by 1. 1/3 minus 1 is negative 2/3. And now we can just substitute in, so we get the cube root of x times 1/2 x to the negative 1/2 plus square root of x plus 3 times 1/3 x to the negative 2/3, and you can simplify that if you want to, but I don't feel like doing that right now. Alternatively, we could have said that f of x equals, we're given that it's equal to this, but why don't we start by converting them to powers? So x to the 1/3 times x to the 1/2 plus 3. And then we can distribute. That's equal to x to the, well, powers add when we multiply like this. So 1/2 plus 1/3 is 5/6 plus 3x to the 1/3. And now we're just adding two functions, so we can compute the derivative as we would normally do. The derivative of the first term, just use the power rule, 5/6 x to the negative 1/6. Second one, you also do the power rule, 3 times 1/3 x to the negative 2/3, and we can simplify this some more if you feel like it, and this just gets us to this. And you can see for yourself that these two are in fact equal to each other. I suggest trying it out for yourself and seeing if I'm correct. I really hope I'm correct, but it seems like it should work. But yeah, that's just another way of computing the derivative. Okay, now we're asked to find the second derivative. Okay, so that means we find the derivative once, then we find the derivative a second time. Pretty simple, right? So this looks quotient rule-y, it seems like we're gonna have to use it. So I'm just gonna write it out here, whatever low and high is. Low is that, high equals x squared plus 3x, right? So f prime of x equals low d high d dx of x squared plus 3x minus high d low d dx of x minus 4, all of this over low. And then I'm not going to write them out separately because we should be feeling comfortable with derivatives now. So the derivative of x squared plus 3x, we're going to use the power rule for x squared to get 2x. And then for the second one, constant multiple you could use, maybe power rule if you wanted to, but you'll get that's equal to 3. I think there's actually a rule that we talked about where it's like c times x, the derivative of c times x is c, minus x squared plus 3x times the derivative of x minus 4, derivative of x is 1, derivative of negative 4 is 0, all of this over x minus 4 squared. Okay, and we're gonna actually multiply it all out. So let me just copy it, copy, paste. So this is equal to, let's multiply the top thing out, 2x squared minus 8x plus 3x minus 12 minus x squared plus 3x, all of this over x squared minus 8x plus 16, right? And then we have this term is common with this term, so this becomes x squared. We have minus 8x and this minus 3x, so that's minus 11x. But we also have this plus 3x, so that's actually just minus 8x. And then the minus 12 comes along. And we're dividing this by this term right here. So that's the first derivative, right? That's f prime of x. Now we have to find the second derivative. Well, we're going to do the quotient rule again, and I'll use a different color now. So now we have low equals x squared minus 8x minus 16, and high equals x squared minus 8x minus 12. So let's do it again. Low x squared minus 8x minus 16, d high, so the derivative of x squared minus 8x minus 12, minus the derivative of high, just high, times the derivative of low. All of this over low, right? And let's just compute the derivatives. We won't worry about simplifying it. So the first term stays how it is. The derivative of x squared minus 8x minus 12, well, derivative of x squared is 2x, derivative of negative 8x is minus 8, derivative of negative 12 is 0, so that's that. And then this term comes along for the ride, and then we have the derivative of the second term, so d dx of 2x is 2x minus 8, all of this over, I forgot to put the square term there, minus 8x minus 16 squared. And if you're feeling like you really want to do a lot of algebra, you can simplify that, but I'm kind of lazy, so I'm not going to do that. But yeah, that's the second derivative, f double prime of x. Cool. All right, do this one next. If g of 2 equals that and that and that and that, find f prime of 2 if f of x equals g of x divided by h of x. Okay, so what's f prime of x? That's just quotient rule, right? So f prime of x is low d high, so g prime of x, minus high d low, h prime of x, all of this over h of x squared. And we want to find f prime of 2. So f prime of 2, that's just equal to h of 2 times g prime of 2 minus g of 2 times h prime of 2. All of this over h of 2 squared. And we're given the values right here. So let's just plug it in. h of 2 is 4, g prime of 2 is negative 2, minus g prime of 2 is 3, h prime of 2 is 4. Actually, this first value is incorrect. H of 2 is negative 1. And we're dividing this by h of 2 squared, which is negative 1 squared. So this becomes 2 minus 12, all of this over 1. So our answer is negative 10. Awesome. So now we deal with the chain rule. Let's see, do we want to get into this today? Let's save this for next time. We'll start with the chain rule next time. But this chain rule, you can start to look at it now. This is going to help us a lot to deal with some really complex functions. I know we've already dealt with a lot of complex functions, but with the chain rule, we're going to be able to expand our toolkit so much and evaluate some really, exciting functions. It's going to help us out a lot. So I'm going to call it a day for that. This lesson was actually kind of long, but hopefully you found it enjoyable. And you should be really proud of yourself, considering how much you've learned in the past hour and a half, right? We started out not knowing what a derivative is, just plugging stuff into limits and hoping that the limits were nice to evaluate, and luckily I gave you some nice limits to evaluate. But now we can easily find the derivative of 3x times sine x times cosine of x times the square root of x plus 1. Like, with what we've learned today, you can now solve that. And in fact, I suggest you to try that out. But yeah, next time we'll get started with the chain rule, and we'll finish up this first unit on derivatives. So yeah, thank you for joining us. If you were joining us live on Twitch, thanks for tuning in. Don't forget to follow. And if you're on YouTube, please subscribe and tune into our streams live so you can ask your questions. And yeah, to the Twitch viewers, this will be posted on YouTube in due time. Tomorrow is Thursday, so don't forget to tune in for AP Physics C content if you are interested in that. And next week, we'll be right back at it. Monday, Physics 1, Wednesday, Calculus. So hopefully you had fun, hopefully you learned a lot, and until next time, take care.